We had single replacement last week. One thing replaces another. So, any guesses as to what double replacement is? Two things replace. And what do they replace? Well, what they do is they replace each other. Two things replace each other. So you start off with compounds. They have a partner. And then the partners switch. Okay, the partners switch. So everybody's got a positive and negative piece. At the end, you got a different positive next to a different negative. They replace each other. So my reactants have to be things that have partners. So I need two compounds as my reactants. The compounds are going to be the types of things that have partners, positive and negative pieces. So they're going to be ionic or acids. Usually an aqueous solution. Aqueous solution means it's dissolved in water. So normally you can't see the ions in the solution, because in a solution of salt water, you don't get to see the ions because the salt isn't there. The salt is falling apart into its positive and negative ions. Okay? You don't get to see the salt until the water goes. So here's the reactants. Two ionic compounds. Sodium hydroxide and iron 3 chloride. And what they do is the positive ions, the cations, change places. It doesn't matter which one you pick. I pick the positive ions because that's the way I've been focusing on so far. Technically, the negative ions change pieces too. In our analogy about dance, this type of situation would happen in square dancing. Okay? The caller goes, swing your partner around and round, pick her up and throw her down. Alaman left, change partners. And that's what we're doing, we're changing partners. You start off with one partner, you end up with another partner. Same thing happens to the other person. So sodium here is starting off next to hydroxide. And iron 3 is starting off next to chloride. So they're going to change partners. So the iron 3 is going to end up next to hydroxide. The iron 3 took the place of hydroxide. The next to hydroxide took the place of sodium. And the sodium took the place of the iron next to chloride. The positive pieces just change place. My cations exchange partners. So this is me doing what the name said, double replacement. Notice I did not bring the little 3 over here, because that 3 is there because iron's got a 3+ charge. I don't bring the subscripts over, unless they're a polyatomic ion. Okay, now that I've got the pieces, I got the charges, I got to do the crisscross. So instead of Fe3 plus and OH minus, it's going to be FeOH3. And I need parentheses because if I don't put parentheses, it doesn't say 3 OHs, it says 3 H's. And 1 plus and 1 minus for NaCl, so that crisscrosses to 0. So all I did in this step was the crisscross. Then I have to balance. Okay? Na, 1 Na, 1 Na, 1 OH, 3 OHs. I'm going to put a 3 in front of NaOH so I can get 3 OHs. Ever see my 3 OHs over here? So now I got 3 OHs. That gives me 3 NAs, so I got to put it in front of 3 in front of NaCl. Not only does it give me my 3 Na, it also gives me 3 Cls, which I wanted anyway. So now it's all balanced. 3 NAs, 3 NAs. 3 OHs, 3 OHs. 1 Fe, 1 Fe, 3 Cls, 3 Cls. Yeah, Valerie. Okay, so I took the positive piece of this and the positive piece of that and switched partners. So the thing in front, the thing in front. This is Na plus, that's Fe3. So the Fe was next to Cl, now the Fe ends up next to OH. And, but here's the trick. The Na doesn't go off by itself. The Na goes next to Cl. So in single replacement, it went off by itself. And you had to decide if it got a 2.
Oh, okay.
Now it's part of a compound. And you got to use charges to figure out how many there are.
Are you always going to take the ones that are in the front and switch them?
Yep. No, I always do. You could take the ones in the back and switch them, but you have to say it doesn't really matter which one you. Metals and metals switch places, or non-metals switch places. Either one's fine. Actually, what really changes is the last name. I started off with sodium hydroxide and iron 3 chloride. I ended up with iron 3 hydroxide and sodium chloride. Just switch the names. Yeah, Mike. Yeah, because it won't work if you think about it. You say, ooh, sodium is above iron, so this happens. But then you're also going to say iron is below sodium, so it doesn't happen. So the activity series, actually the one I gave you on the test, actually said 4 single replacement reactions, because that's the only place it works, is in single replacement. Here, we're going to talk about other reasons why this happens. And the reason why it happens is it gets rid of ions. We get the ions out of there. And there's specific ways. But in terms of square dance, there's our partners. I got 3 NAs next to OHs. And I've got an Fe3 plus surrounded by Cls. And then they change partners. So now I've got 3 NAs next to Cls, and Fe3 plus is next to 3 OH minuses. Make sense? Hugely different than what we're doing before? Nah, it's all about crisscross still, right? Well, now you don't have to worry about the 2s. Now you just have to worry about the crisscross, because everything's going to be a crisscross on the other side. Okay. So we can't use the activity series. So we actually look and see, we have to figure out what the products are going to be and then figure out something about the products. And the things that make it happen are things that separate the ions from solution. Something that gets the ions out of solutions. Okay? And as long as it's dissolved, it's in solution. So we have to undissolve it. So the most common reason why these things happen is because it makes something that doesn't dissolve in water. And that thing that doesn't dissolve in water forms a solid. These are the things that we talked about at the beginning of this chapter, where we can use a downward arrow to say they were solids. Because if I make a solid inside my aqueous solution, what's going to happen to that solid? Well, it's going to sink down to the bottom, right? The name for that solid is a precipitate. Same root word as precipitation. Precipitation is snow and rain and sleet and hail, the things that fall down out of the sky. Precipitate is a solid that falls down out of the solution. To give you an example of this, find that camera. There it is. Okay. Over here I got a test tube rack and some test tubes, so empty test tube. In it I'm going to put some PbNO32. That's a little too bright, you can't see it. This is PbNO32. Nice clear solution, right? Nice clear solution of lead 2 nitrate. And next into that I'm going to pour some potassium iodide, some Ki, another clear solution. But when I pour it in, it's no longer a clear colorless solution. That is not colorless, and it's not clear, it's opaque. Okay. The fact that light doesn't go through this, that it's cloudy, tells you you made a solid. That's what's blocking the light, is the solid you made. It's just going to take a while for those solids to settle down to the bottom of the flask, or the bottom of the test tube. I did it last period. Here's what it looks like after an hour and a half. See how the yellow's all cleared up and solid sitting on the bottom? Ever see why we use a downward arrow to say precipitate? So that one's going to look like that one real soon. And the fact is, it's starting to settle already. See how it's starting to move down? Slowly but steadily. Over time, this whole top will be clear and the bottom will be just solid yellow. Okay, so precipitate, separate from the solution. Another way things separate from the solution is to become a gas. If that gas bubbles out, you have separated something from the solution, so you're going to have a reaction. And then there's a bizarre one. You make something molecular instead of something ionic. And it says, usually water. It's hard for me. I can only think of examples where it's water. And water is covalently bonded. It's a molecular compound. It doesn't have charged pieces. It shares electrons. So what's happening here is, I had some things that were dissolved in water, and then they became the thing they were dissolved in. They became the water. They started off dissolved in water, but they made water, so they're no longer being dissolved. They are the dissolving thing, which separates them from the solution. Polyatomic ions are things that have a charge and stay together. They're going to stay together and keep that same charge from one side of the reaction to the other. So the only subscripts you should copy are the ones that make up a polyatomic ion. Just the stuff that's on the yellow sheet. No parentheses. Shouldn't copy any of those pieces. For example, and for right now, we're going to assume all reactions take place. Later on, we'll learn how to predict whether they take place or not. That would be part of that ionic stuff you talked yesterday. We read that about last night. So we're going to assume all these take place for right now. So CaCl2 plus NaOH. Okay. The positive pieces are the pieces in front, the calcium and the sodium. The calcium is going to replace the sodium, and the sodium is going to replace the calcium. They replace each other. So the calcium was next to chlorine. It's going to end up next to OH. The sodium was next to OH. The sodium is now going to be next to Cl. I did my double replacement. Now I need to do the next step. Figure out the little subscripts. Na is in group 1a, so it's 1 plus. Cl, the halogen, is 1 minus. NaCl is the right formula. I look at the chart. Ca is in group 2a, it's 2 plus. OH is on my polyatomic ion list as 1 minus. That doesn't add up to 0. When I go to do the crisscross, I want to put a 2 here, but I got to be careful that I put parentheses around OH. Because I don't want 2 H's, I want 2 hydroxides. I want 2 of those polyatomic ions. I want it to stay together, because OH is that piece that stays together. So first I do what the name says, double replace, then I figure out subscripts, then I balance. I got 2 CLs, so I got to put a 2 in front of NA. CL on the other side. That gives me 2 NAs, so I got to put a 2 in front of NaOH. That gives me 2 OHs, which I wanted anyway, because I had two OHs on the right-hand side. These should balance fairly easily. If you find yourself changing numbers and going around in a circle, you got one of these subscripts wrong. Because if you get one of those subscripts wrong, you're talking about something with a different charge. And the only way to get that different charge would be to create or destroy electrons. And matter can't be created or destroyed. It doesn't have to be the whole atom. We can't even create or destroy an electron. So if you got the subscripts wrong, it usually doesn't balance. Unless you made them all ones, which is kind of trivial. Okay, so let's talk about what we did right there. Let's try to figure out what the heck I made there. Okay, so I said I put together lead 2 nitrate and potassium iodide. So that was what those 2 clear solutions were. They were both aqueous. You didn't see lead nitrate or potassium iodide because they were dissolved in the water. What are we going to make? Well, the positive pieces are going to change place, so lead starts out next to nitrate, so lead is going to end up next to iodine. Potassium starts off next to iodine, it's going to end up next to nitrate. So I did what the name says. Did my double replacement. Now I got to worry about charges. K is 1 plus, NO3 is 1 minus, so KNO3 is the right formula. I is 1 minus, it's a halogen, group 7A. PB, I can't get PB from the table, but I can get it from over here on the other side. Okay, on the other side, since nitrate's minus 1, I got a total of 2 minus, so the lead had to be 2 plus, right? So if it was 2 plus on one side, it's got to be 2 plus on the other. That doesn't add up to 0, so I do the crisscross, I get PbI2. Did what the name says. Got the right subscripts. Now I need to balance. I've got 2 NO3s over there, so I put a 2 in front of KNO3. Gives me 2 Ks, so I put 2 in front of Ki. Gives me 2 Is, which I wanted anyway. So we're done. Hugely different than what we've been doing. Okay, so right now, that yellow stuff is one of those 2 things. Man, we know it's got to be one of those. It's either lead 2 iodide, or potassium nitrate. Because we know we made something. One of those is yellow. Yeah? We already did this one's just like the first one example I gave you, so let's just do this last one. H3PO4 plus CaOH2. Okay, and the positive pieces are going to change place. So the H and the Ca are going to change places. So the H starts out next to PO4. I don't want it next to PO4. It's going to end up next to hydroxide, OH. And Ca was next to OH, now Ca is going to be next to PO4. So I put the P, did what the name said to do. I did my double replacement. Now it's time for subscripts. Phosphate on my list is 3 minus. Calcium is in group 2A, so it's 2 plus. That doesn't add up to 0, so it's got to be Ca3PO42? Nah, PO4, 2. H is 1 plus. I look up OH on the chart, it's 1 minus. That adds up to 0. Water, you think that is? Yeah. It's water. We know this reaction is going to happen because it made water. Now, calcium phosphate may also be a solid, but we know it's going to make water. Ever see how we know it's going to make water? HOH. And I want to leave, and it's okay to leave it written as HOH here because it makes it easier to balance. Because I can count OHs instead of O's and H's. So if I start counting O's and H's, look at all the O's in there. Look at all the H's in there. I want to count polyatomic ions. So I have 3 H's in front of H3PO4. So I'm going to put a 3 in front of HOH to give me 3 H's. That gives me 3 OHs. That doesn't do me any good. Okay. Let's move on. Oh, it says 3 calciums on the product side. So I'm going to put a 3 in front of calcium phosphate. Calcium hydroxide, sorry. And that gives me 3 CAs, but it gives me 6 OHs. So if I want 6 OHs, this can't be a 3 in front of HOH, it's got to be a 6. That gives me 6 hydrogen. To have 6 hydrogen, I'd have to put a 2 in front of H3PO4. That gives me 2 PO4s, which I wanted anyway. So this equation is now balanced. It's got 6 H's on both sides, 2 PO4s on both sides, 3 CAs on both sides, and 6 OHs on both sides. See how it's easier to count OHs and PO4s than O's, H's, and P's? Because they're going to stay the same on both sides. So hugely different than what we've been doing for a week? Nope, just one more step, right? So let's do one more step. See if we can step up. Good news. No, backside.